Good morning. Debbie, we were listening to John Denver and Sunshine? What? No.
Yes.
Sunshine? Yeah, and it is nice outside. Yeah, we get a sunny day like this, and we have a small number in here this morning. We have some new material that we are going to talk about. And let's see if we can cut to a camera here. And let's go to that much. Solving quadratic equations. Okay, so solving quadratic equations. And the question, of course, what methods are we going to use? So as we come off there, the first one that's talked about here is the square root property. Now, I'd like to put into context where we've been and where we're headed. So as we come off there, how did we solve quadratic equations before as a rhetorical question? And the answer, so let's look at a few equations of the type. Let's say that I had x squared minus 3x plus 2 equals 0. You'd factor. X minus 2, x minus 1. We have a product equal to 0. The argument by the zero product rule, if this product gives you 0, then we argued one or the other of the factors must be 0. So that gave us an x equals 2 or an x equals 1. And with a problem like this, it was a matter of substitution to check the solution worked, but you, for the most part, didn't need to worry about whether or not you had extraneous solutions. Reason? You hadn't done anything to introduce new solutions. The one important issue here, 0 on the right side. Okay, so the original problem might have been written something like this. But the first step would be to bring everything on one side equal to 0. In a sense, I'm going to put a couple check marks here. That is an important step to factoring, but it's a more important step to a general form of solution we're going to introduce in this chapter. We've talked about it before, where I can get the form of an equation in a general way as little a times x squared plus little b times x plus little c. And so the argument we make is that if I can get it in that form, we are going to introduce ultimately a quadratic formula, which will argue that if you know these coefficients, a, b, and c, we will be able to substitute into this formula and get our solution. And that's known as the quadratic formula. So that's where we're headed ultimately in terms of solving a general second degree equation that we have set equal to 0. So we could solve this particular problem using that equation. In fact, this is a sledgehammer, if you will. It will take care of any second degree equation in one variable. The factoring process works so-so. Okay? Now there's a particular class of problems that we can write that have a fairly interesting shortcut. Now there's x squared minus 9 equals 0. We can certainly factor it. It's the difference of two squares. And so I can rewrite it as x plus 3 times x minus 3. The sum and the difference. And by the way, we've called that a conjugate, right? If we had a plus b, we talked about the conjugate a minus b. Then, again, I can argue that the factors can be set equal to 0. And then that gives me the two solutions. That process can be generalized in the following way. If I have x squared minus 9 equals 0, we argue that I can just isolate the x squared by itself and then take the square root of both sides. So the square root of x squared and the square root of 9, but we have a little wrinkle we have to introduce here. We note from what I did in factoring that I had two possible solutions, a positive and a negative. So what we do is write a plus minus sign with the square root of 9. We argue that the square root of x squared is just x. And when I take plus or minus the square root of 9, I get the two solutions that we referenced right up here. But now we write them as x equals plus or minus 3, which is interpreted as x equals 3 or x equals minus 3. Okay. Now that allows us to carry through a problem we had looked at earlier. This is going back a ways. But at that, maybe at least 3 weeks ago, maybe a month ago or plus, I said, we actually can factor this. Now, we usually think of factoring using integers. And so this may seem uncomfortable to you. But if you think of what's involved there, x times x is x squared, this inner and outer product will go to 0. And the square root of 2 times square root of 2 is 2. So it does provide a correct factoring, and so I could argue that x minus the square root of 2 is equal to 0, or x plus the square root of 2 is equal to 0. So that allows me to say x is equal to the square root of 2, or x equals minus the square root of 2. And so with that done, I could go back and say, as a shortcut, I could just argue x squared equals 2, and using the technique that's involved here, say then that x is equal to plus or minus the square root of 2, which again is the solution we had. Okay. One of the arguments that we make in algebra has to do with how many solutions we have for certain types of equations. In this case, we have a second degree equation. We want two solutions, and we have them. But we had to go to the set of real numbers, more technically to the irrationals, rather than just in the set of integers that satisfied the other equations we've looked at this morning. This brings up the question of what happens if instead of having a negative, I have a positive. And we've talked about this before. The idea in this case is that I want two solutions. Well, factoring this in the usual sense of the word doesn't seem to lend itself to very much. If we approach our new technique, which is to say isolate the x squared, then I have x squared is equal to negative 1. And then that says that x must equal plus or minus the square root of negative 1. If we're going to have two solutions, we're going to have to identify what the square root of minus 1 is. And we are going to identify that as little I. And this was done so that, theoretically, we have consistency. Every equation, second degree, one variable, is going to have the potential for two solutions. Okay? Now, I have to be a little bit careful that I'm going to look at another problem in a moment. But what we argue now is that we get plus or minus I for the solution. And this puts us into imaginary numbers and more technically into what we call the complex numbers. So we extend our number system. We started the semester talking about the real number system. And we are finishing the semester introducing the complex numbers. As long as we stay in the set of reals, then I would say at this point, no solution in the set of real numbers. However, if I extend the allowable numbers to be the complex numbers, then we will have two solutions. So this chapter, we play little games. At the beginning of the chapter, we say, here's where we are. At the end of the chapter, we say, oh, now we're going to go here and have complex numbers. But for the moment, the approach is going to be x squared. If it ends up being equal to a negative number, then you will not have a solution temporarily. But we would like that completeness. Any second-degree equation, one variable, has two solutions. And so we will create a new system to make that happen. Okay. It's in the same spirit, by the way, that the square root of 2 required that we extend, as we slide over, Debbie, to what we had here. When we basically extended our system to allow for the square root of 2 and say we had irrational numbers, that was a very traumatic period in early Greek mathematics, because they wanted numbers to be, at worst, a fraction, not something like this. And this was very much a case of reality forcing a new system of numbers, because this is the diagonal of a unit square using the Pythagorean theorem. If you have a unit square, 1 by 1, and you take the diagonal, you have Pythagorean theorem, 1 squared plus 1 squared is 2, and the diagonal squared is 2, and this just becomes a measurement of a problem that was somewhat fascinating to early mathematics. So this process of going from integers to irrational numbers and then to complex numbers is a logical progression. Now, in the text, the problem is extended to a little different form, and I'm going to have to, in a moment, go to the sideboard for that. If we come back to the text for just a moment and allow Debbie to get some adjustment of the camera there, what we're seeing there with the square root property is extended to an equation of the following form, and I'll zoom in on this. Okay, this is the form we're talking about. X plus b quantity squared equals a constant. Now that one's not quite as easily seen in terms of the kind of problem we are talking about. And you need to understand that there's two different issues involved here in this problem. One, if I see a problem like this, then I know what to do. But more importantly, maybe I can translate every problem into something like this. It's not as innocent sounding as it appears. Now, as we look at example 2, this is on page 579, I don't think you can probably sit there and honestly say somebody's going to walk up to you and give you an equation in that form. That's nice of them to do so, but reality is not going to happen. So as we come off there, the question is, why would you even have an equation like that? And I'm going to try to make a little bit of a effort here to see if we can take what is not so obvious and make it a little more obvious. Let's come back to the example. The goal is, 1, to be able to solve the problem, 2, to see where that might arrive. Okay, let me first write the equation. And of course, it's rather nice that the right side is a what? A perfect square. That makes life much nicer. So I'm going to have x minus 3 in the left side, plus or minus the square root of 16. That's the process. And so that gives us x equals, and I'm going to write it this way. Now I could have simplified the 16 in the root, the square root, to a 4. But this is 3 plus or minus the square root of 16. So this says I have 3 plus or minus 4. So that says that x is equal to 3 plus 4, or x equals 3 minus 4. Do you understand what I did there in that process? So this gives me a 7 or a negative 1. Now I'm going to do something a little bit different here. I'm going to square the left side, and let's see what that equation would have looked like if I didn't have it in this form. If you didn't have this new section, you might have been inclined to do this. Simply square the left side. Remember, that's a trinomial perfect square. So the x squared, then you take the product and double it and square the last term. This is x minus 3 times x minus 3. So it might help if I write that up here first, just so you can see that we indeed, by taking the outers and the inners, end up with a negative 3x in each case, had the shortcut doubling the product. If I had gone ahead and done this as usual, I would have probably simplified it in this way and said, aha, I can factor. And an x minus 7 and an x plus 1 would have done the work. So I would have said x minus 7 equals 0, x plus 1 equals 0, and then said x equals 7 or x equals minus 1. And I hope what you realize we're getting the same solution in both cases. Now, the process I did said, let's go this direction. Take the original equation, expand, bring it back so everything's equal to 0, and factor. I'm going to start right here and say, if I had something like this, could I in some way get it back to, and I'm going to write where I'm headed. Remember we had this at the beginning. Could I in some way get back to that? That's the argument. Otherwise, I'd like to write the left side as a square of a binomial. So if I do that, the first thing is to bring the constant to the right side. Now, I'm working backwards, and I'll tell you right up front, this is the difficult step. I want to add something on the left side so that the left side is a trinomial perfect square. So I want whatever I put here so that the left side is a trinomial perfect square, TPS. Now we know, from what I can see right here, what that question mark has to be, correct? The 9 works, just by comparing. Is there a way of getting that number magically every time? The answer is yes. What I want to do is double, I don't want to double, rephrase that. Excuse me, Debbie, while I get an eraser for that. I'll rephrase what I want here. I want to take 1/2 of the coefficient of x. So what is that going to give me? -3, correct? Then square that result. Okay, so 1/2 of the coefficient is -3, and square that, and I get 9. Okay. So to get the question mark, so what I did is take 1/2 of the 6, squared that, that was a 9, add it to both sides, and I get this result. Okay. So what I'm going to have then is a 9 added here, and then I can rewrite the left side in the form I want it, and the right side is 16. We with it? We have a name for this process. Which I hope makes some sense. Completing the square. That's what it's referenced as. Okay. Let's look at another one just to see if we get the idea. Okay, this one I've got to think what I want here. Let's take x squared minus 10x minus 11 equals 0. Now I think you can see how the factoring is going to go. Can you factor that in your head for me? And have an x minus 11, an x plus 1, so you can have an 11 and -1 for your solutions. So note, that's the factoring. Now, the interesting thing is not that I can do that and get the solution. That you should feel pretty comfortable doing. But now the question. Let's try completing the square. Okay, x squared minus 10x plus a question mark equals 11 plus a question mark. What do I need for the question mark? Half that's 10 is 5, and then you're supposed to square that.
So 25.
25. So I'm going to say x squared minus 10x plus 25 equals 11 plus 25. Do you see why I took the 11? 36 is a nice perfect square. So I tried to rig this so it would work nicely. Now what am I going to do with the left side? I added the 25, so this was what? What was the goal? To get a trinomial perfect square. This is just x minus 5 times x minus 5, which you're more inclined to read as x minus 5, quantity squared equals 36. Then you take the square root of both sides. Pardon? Well, not yet. I mean, we're getting close. X minus 5 equals plus or minus 6. And because I'm running out of room here, we would say x equals 5 plus or minus 6, which means x is equal to 11, or x is equal to -1, and I have the same solution. Is there any question in the process there? Now, the whole idea in what's being done in the text is to give you a bunch of problems that are in this form. Like, you have no idea where that ever is going to come from, but you just get comfortable doing it. Okay. Now, there's another problem I'm going to adjust here a little bit. If I had instead 2x squared minus 20x equals, okay, let me see what I want to do here for a moment. Trying to think what I would like here. And if I add that and I subtract, I'm wanting to do something that gives me a different solution here. So I need to adjust it. I don't want the 36 this time. I'm going to have a 25. So if I take something from 25 and get down to a 16, I would have a positive 9. So let's make this a negative 18. So maybe I'd have something like this as my first step. Now my point is, you want x squared by itself, so what are you going to do? If you wanted x squared by itself, try to divide everything by 2. So I would divide the left side by 2, the right side by 2. And in fact, if I'm going to do this and make it work, I'm going to make that a positive, so this becomes a negative. So I have positive 18, so I have a negative 18 over 2 on the right side. Now this gives me a negative 9 on the right side, and you'd again add what to both sides? 25 as before. And the left side again is the nice form we want. The right side is the 16. And life is good again. So x is equal to 5 plus or minus 4. So x is equal to 9 or x is equal to 1. Now the reason I bring this up, if you see something that doesn't start with x squared, what do? Make sure it does start with x squared by dividing by the coefficient. Okay. Any questions so far? Okay, what I'm going to do is walk off camera here. I'm going to go back to the book. And we're going to look at the kind of problems that are done in the text at this point. If we look at page 581, and first coming back to the 13, 17, 21, 14, 18, 22, they're all pretty straightforward. Take the square root of both sides. This is on page 581. Okay, let's come off there for a moment. Look at what happens as I get down into a little more complicated problem. 25, 28 are just exactly what we've talked about. But notice 31 and 34 are new wrinkles. A little bit different than what we've done up to where I just stopped on the side board. Well, let's look at 34 for a moment. In number 34, if we just look at this problem, and for those who are watching on the videos, we're going to take the square root of both sides. So we have 7y minus 5 equals plus or minus 5. And then it's a matter of solving for y. Okay, so let's come off there for a moment, Debbie. And let me pile some chalk on there to make sure. Let's come back to the paper. Now I have up here on the board what I'll write as the same number. I have 7y minus 5 quantity squared equals 25. Now, there needs to be some intermediate step here. You could just about do these in your head at this point if you see the shortcut. But it's a little bit better to say 7y minus 5 equals plus or minus the square root of 25. I'd like you to have that as an intermediate step. Now, at this point, 7y is equal to 5 plus or minus 5. And what I could argue is that y is equal to what? 5 plus or minus 5 over 7. Now, you can argue that that's 0 or 10/7. So certainly, this is the answer to this problem. But my question, what would happen if the text had not been so kind to you and given you 25 here? Something that didn't have a nice square root. Well, let's say it had been something like this. A 26. Same argument. 7y minus 5 equals plus or minus the square root of 26. And I can't do anything with the square root of 26 at the moment. So if I look at this solution in exactly the way I did this one, then I would say that y is equal to 5 plus or minus the square root of 26 all over 7. Okay? Now, Debbie, using camera 1, would you go to the quadratic formula, bottom left side front board, where we have x equals minus b plus or minus the square root of b squared minus 4ac. What I'm going to do is contrast the form I had there with what we have right here. Now notice, in this case we have 2a in the denominator. In the one I have on the side, we'll have Debbie cut back to that, we had 7 in the denominator. In this case, I have minus b plus or minus a square root. So what we see on the sideboard is a 5 plus or minus the square root of something over 7. It's exactly in this form. Okay? So the point I'm making, you don't always have the luxury of doing what? Simplifying the radical. It's nice when it does, but it's okay when it doesn't. And if you look again at the sideboard, that solution is an acceptable solution in just the format it is. You would not be required to go ahead and rewrite it as 2 separate solutions. That is acceptable. If I look in a moment here at a problem that's given to you in the text on page 581, this is number 43. The statement that precedes what you're seeing, Johnny solves the equation and wrote his answer in the following way. And then, of course, what they do is they have Linda does it in a slightly different manner. But my point is that particular answer written as 5 plus the square root of 30 over 2 and then 5 minus the square root of 30 over 2, if I come back to the sideboard, then in the same way, I would have that equation as a solution 5 plus the square root of 26 over 7 and 5 minus the square root of 26 over 7. Now coming back to the problem in the book. Do you see what's been done there? The minus signs? Otherwise, as I look at that, and it's just a little bit confusing because it looks like a flip-flop has occurred here. Here both the 5 and the square root of 30 are positive, and here they're both what? Negative, and you have a negative in the denominator. Here you have a positive 5, a negative the square root of 30, so if I multiply top and bottom by -1, I get the first value. Now, I would want you to understand that this, as a pair of numbers, there's nothing gained by flip-flopping the order here and here. I don't see any particular gain there, and nothing is wrong with one or the other. One of the issues that interestingly comes out of this effort, and I'm going to come back over in the sideboard here in a moment, but one of the problems, if we have the square root of 26, you get so much in the habit of seeing that you don't understand that there is a step that can be done. So we're going to go to that side problem again, Debbie, if you'll bring up the problem on the sideboard. The question, the square root of 26 you would find in a calculator. And so what you could do right here is take this and argue that you're going to take 5 plus, now the square root of 26 is going to be 5 something. Let's see what it would be. If I take 5.2, about there. Somebody have a calculator handy? I'm trying to estimate that in my head. And what do we have in that? Michelle, if you could. We have 26 and take the square root. 5.09. 5.09. So if we had 5.1, then you could add those two together and divide by 7 to get a numerical value. So that's going to be 10.1 over 7, which is going to be a 1 point, and I'm just going to put a plus there. You can find the numerical value. We get so much in the habit of just writing 5 plus minus the square root of 26 over 7, we may forget that that represents a number. Now, if I have 3/7, my guess is that that's 1.4 something, and so we can get a numerical value for it. So let's go back to the document camp. Those numbers in the same way could be simplified with a square root symbol, and that indeed, as we come off there now, is what you're asked to do in problems such as 46 and 48, where it's assumed you've done what? You've taken the square root in the right side and you have a particular value. Now, that isn't something that we will do very much about in the problems we do, because in the process, we are more interested in a technique here than we are with an answer. I just know that sounds awkward, but we aren't so concerned about that numerical value. The technique I followed through, called completing the square, is really what's involved here and is more important in some ways than anything else we did today. In fact, if we go to 583 and we look at the directions or the statement here, it's solving by completing the square. That is the process that's involved. Now, here's the challenge in a way. If you start with the generic version of the quadratic equation. So Debbie, what I'm going to do, let's take camera 2 now, bring it back around over here, and ultimately what I want to do is get to the ax squared plus bx plus c equals 0. We'll go to that in a moment. And ask, how do we generalize that as a process? Because it's something I want you to be able to do, and it isn't something done in the text, unfortunately. They have reduced the complexity of the text. The closest we can come to that as far as what's involved is on page 590, where we actually get, as we cut to there now, the quadratic formula. Now that's going to contrast with what I have back here. And so what we have is an ax squared plus bx plus c equals 0. We want to get down to here. Now the first thing I would need to get x squared by itself. So let's just outline the steps mentally that would be involved. And I'm going to have to punt here, Debbie, a little bit. Let's come to camera 2, right side middle panel where you have a 2x squared minus 20x plus 18. And I'm going to try to mentally ask you what would happen as you go through these steps. So can you cut now to 2x squared plus or minus 20x plus 18 equals 0. We'll just cut to there for a moment. Now in that process, and I'll sort of walk back and forth between these two boards, what was my first step here? Divide by the 2 to get rid of the coefficient. So I want something just with x squared. So if I had, now Debbie, with camera 1, give me ax squared plus bx plus c. And we're going to be running back and forth here. I would divide everything by a. Okay, and that has something to do with why you're seeing the a in the denominator when you have x by itself. We divided everything by a. So when I think of that, let's come back to here. Now, I've done that step. Then what did I do? I tried to complete the square on the left side. That was the process I went through. So let's come back to the text again so I can give Debbie a chance to move cameras around. And I'm going to go over to that little space I have over in this right side. So I'm going to put what we had in our next step. I started with this, ax squared plus bx plus c equals 0. Then I divided by a, correct? So I'm going to have x squared, b over a times x, and I'm going to do 2 steps at once here. The minus c over a. C goes to the right side, it becomes negative c, and I divided by a. Okay, back to my the other problem we were at on the other panel, which was the 2x squared minus 20x, etc. Once I had x squared by itself, then I did what here? I took this coefficient divided by 2, squared that number, and added it to both sides. Okay, with camera 1 back to my little list. What is b over a divided by 2 going to give you? b over a and divide it by 2. What would you get? b over a divided by 2. Would you buy b over 2a? b over a, you divide it by 2. Invert the 2, it becomes 1/2, multiply, and you get b over 2a. Okay, now square b over 2a, and what do you get? b over 2a and square it. b squared over 4a squared. So far okay? Now if I've done this correctly, I should be able to write the left side as something squared. And we know it should have an x in it. And then what? Okay, let's go back to the sideboard. This is pushing things a little bit. What did I get when I divided by 10 by 2? I got a 5. And that's what I put here, right? So if I have 10 divided by 2 and get a 5, I put the 5 here. Okay, back to the front board. So what am I going to put there inside that parentheses? AB over 2A. So I have x plus b over 2a. And then in the right side, what do I have? Well, I have minus. I'm going to write it this way for a moment. That's what I have on the right side. Now question. If I'd like to combine these two with the same denominator, I'd have a common denominator, correct? Which is 4a squared. So if I multiply this first one by 4a top and bottom, okay, then I'm going to get b squared minus 4ac over 4a squared. Again, multiplying top and bottom here by 4a. Let's see if I can get some space there. Let me first, what can I do here? I'm going to put complex numbers down here. And I'm going to get myself some space here and say I'm multiplying by 4a top and bottom. Now does it make more sense to you as you see it? Same denominator, 4a squared. So now I have a b squared minus a 4ac all over 4a squared. Now, Debbie, camera 2, front board, right bottom, quadratic formula. Here's my b squared minus 4ac that we talked about. And there's the square root of 4a squared. Okay. Now, let's go back to the equation on the right side of the board. If I take what I have here, I'm going to put in a box. Well, a trapezoid. Okay. Looks like an old IBM card, nearly. Now, in this case, I have something squared to the left. Can you picture taking the square root of the left side? You'd have x plus b over 2a. So the left side would be x plus b over 2a. And the right side, you'd have the square root of that mess, which we said is b squared minus 4ac all over 4a squared. You've taken the square root of both sides. When you subtract b over 2a from both sides, you're going to get what we have on the right side of the board. This is minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. This formula comes out of completing the square of this general equation. Now, that's not done in your text for you. But what I'd like you to do as part of tonight's homework is try to carry through those steps we have outlined. Start here, divide everything by a, complete the square, and ultimately try to get down to x. The steps we just talked about. Now, what I'm going to try to do for you in terms of the presentation here, so this isn't going to be something that you see for the first time in your life, on your own totally. I'll try to carry that through in steps, and we'll use the document cam as sort of an in-between process here, and see if we can make some sense out of this. Because this takes a few days to do and get comfortable with it. But it's something I want you to be comfortable in doing. There's my equation. ax squared plus bx plus c equals 0. So that's where you're going to start. Will you write that down on a fresh piece of paper now? So I'll let you write that down first. Okay, coming off there. Now I'm trying to get that as sharp as I can and darken it down a little bit. Now my next step is to divide by a. Now I'll show you what I get. And I'm going to not put two steps together. Okay? Then I did what in the next step? Get the c over a in the right side. Okay, so let's come off there for a moment, Debbie, and I'll just write in what I'll have as the next step, and then we'll come back to the document cam in just a moment. So this is all I've done, as I have subtracted c over a from both sides. Now this is the next hard step. I'm taking b over a, dividing by 2, and arguing that that's b over a times 1/2, which is b over 2a. Now, I hesitate to, in this process, use an x. But I took b over a divided by 2. That's the same as b over a times 1/2, which is b over 2a. Now, my rule is square, so add square of b over 2a to both sides of equation. So here is my statement. Add the square of b over 2a to both sides of the equation. Now, the square of b over 2a is b squared over 4a squared. So this is what I'm going to add and subtract to both sides. So I'm going to write that in a moment. Added to both sides. So what I'm going to have in the next step, let me write it out first. And then I'll show it to you. Okay, I need to get the camera up a little bit. That got a little bit longer than I had hoped. Get it in focus. Let's try that, Debbie. Now that is adding b squared over 4a squared to both sides. Now from then on, nothing new happens. All I'm doing is rewriting the form on both sides. Okay, so the left side we're going to write as a binomial squared. So let's come off there. The left side I'm going to write in the following way. Okay, let's look at that, Debbie. X plus b over 2a quantity squared. Now the right side, I'm multiplying a 4a times the negative c over a, both top and bottom. So let's come off there for just a moment and I'll write that in. Okay, you can see what I've done there. I've multiplied by 4a. So what that allows me to do in the next step is to write b squared minus 4ac over 4a squared. Debbie, I guess I'm going to have to move the camera out a little bit to get that. There, looks better. That's what I ended up with. I rewrote the right side over the common denominator. Now once I get to that, what can I do with what we did today? I can take the square root of both sides. So as we come off there, I'm going to have x plus b over 2a equals a plus or minus, and I'm going to do a little simplification here in an intermediate step so you can see it. Okay, let's go to that one. I took the square root of 4a squared and wrote it as 2a. One more step. We're nearly done. I'll write this out. I'm leaving the last step undone. Okay. Now all I did was bring the b over 2a to the right side, and it became negative b over 2a. But I have the same denominator, correct? And that is exactly what I had right here. Minus b plus or minus the square root of b squared minus 4ac all over 2a. Now what I'd like you to be able to do by the end of the week is what we just did going through this page. Okay? Be able to write the quadratic, we'll start with ax squared plus bx plus c and get to the quadratic formula at the end of the page. Let's go back to the paper, Debbie. Minus b
Oh, okay.
plus or minus.
I realized what I did. Okay.
Square root of b squared minus 4ac.
Okay.
I don't have the 4ac there, do I? There I do now. The 4ac, I didn't realize I'd left off that c, minus 4ac all over 2a. Okay, and then I just combined over the same denominator.
I didn't realize you did that.
Okay, so we're going to work on that again tomorrow and then again on Thursday and just continue having fun. The homework is a fairly light set of problems. We're going to start on number 13. Let's see, as we just look at what we have there. This is on page 581. We'll start with number 13 and we will go down to number 42, the odds. 13 through 42 odd. So it's a light assignment. And what I'd like you to do is try carrying through the quadratic formula. Yes, Jennifer?
Through all of them?
Odds.
Yeah, but the quadratic formula, do you want it through all of the problems?
No, the method I'd like you to use on these problems is what we started the hour with. You take the square root of both sides. You don't have to use the quadratic formula. You just, for example, if I look at number 14, y equals plus or minus the square root of 121. That's y equals plus or minus 11, and you're done. Okay? So it's pretty straightforward. With that, Debbie, we started with John Denver, closing.
John Denver, Rocky Mountain High.
And definitely we're doing algebra at that time. Have a pleasant morning.